Hello, everyone. Today we're going to go over Chapter 1, Section 3, Problem Solving with Sets. Thinking about objects in groups is a natural step in trying to understand the world. For example, we could study the set of paintings that an art collector owns. In the language of mathematics, the most basic tool for categorizing objects is the set. We begin by developing a language in which to discuss sets. With that language, we can discuss how sets are related to one another. We can then use our understanding of sets to understand relationships between the groups that we collect in the world. So what is a set? A set is a collection of distinct objects called the elements of the set. So a set is made up of elements. A set can be defined by describing the contents or by listing the elements of the set. We enclose the list of elements in a set by curly braces, called set braces in this context. So the curly braces are what we use to denote our set. This being a math class, it should not surprise you that most of the sets that we will work with in this class will be sets of numbers. However, there is no restriction on what kinds of elements are in a set. For example, we can define the set S as a chair, 42, red. The set S has three elements: a chair, the number 42, and the color red. When we list the elements of a set, the order is not important. The set 1, 2, 3 is the same set as the set 3, 1, 2. When listing the elements of a set, no element should be repeated. So it would be wrong to claim that 1, 2, 3, 1 is a set. The 1 is repeated. Once it's in the set, it's in the set. It does not get repeated again if it comes up again. The symbol, this curvy E looking thing, is the element of relation. X curvy E capital A means that X is an element of set A and is often read simply as X is in A. To say that Y is not in set A, we can write Y and then our curvy E with a slash through it, capital A. That would be Y is not in set A. So if we define capital E as the set of all even numbers, then 12 is an element of E, and 31 is not an element of E. The set which contains no elements is called the empty set and is denoted by a 0 with a slash through it, or just empty set braces with nothing inside. Sometimes a collection might not contain all the elements of a set. We can describe the smaller collection as a subset of the larger set. A subset of a set A is simply another set that contains only elements from the set A, but does not necessarily contain all of the elements of A. For example, the set of all students in an 11 o'clock math class is a subset of all students who are enrolled in a math course at the institution. And that is itself a subset of all students at the institution. If B is a subset of A, we write B, and then that weird looking C with a line under it, A. Formally, we can say that for every x that's an element of B, x is an element of A as well, because B is a subset of A. Everything that is in B is already in A. Consider the set n sub 0 of all odd numbers. I guess that would be n sub O, O for odd. And the sets A equals 1, 3, 5, 7, 9, and B equals the set 1, 2, 3, 4, 5. A is a subset of n sub O, but B is not a subset of n sub O, because 2 is an element of B, but 2 is not an element of n sub O, the set of all odd numbers. Our primary interest in sets is their interaction with each other. So remember a couple lectures ago, we were talking about the Boolean operators and or. And I used the example of two clubs, club intersection, which let in young and blonde, and club union, which let in young or blonde. And club intersection was a more exclusive club, whereas club union was less exclusive. It let more people in. The naming of those clubs came from these terms. We may want all of the elements in which are in both set A and set B. We call this the intersection of A and B, and write it A upside down U B. Alternatively, we might need every element which is in either set A or set B. We call this the union of A and B, and write it A U B. Now that U and the upside down U, the intersection and union symbols, they're a little bit bigger than a typical letter U. So you're not actually writing a U, you're writing a U symbol or an upside down U symbol. Once again, using the sets A being the set 1, 3, 5, 7, 9, and B being the set 1, 2, 3, 4, 5, we can calculate that A union B would be 1, 2, 3, 4, 5, 7, 9, because A union B will contain all the elements of A plus all the elements of B, because you make it into the union if you are in A or if you are in B. And we can calculate that A intersection B is just the set 1, 3, 5, because you make it into the intersection if you are in set A and set B. It is more exclusive than the union. When working with sets, we either explicitly or implicitly usually work within some universal set. Now, the universal set contains all of the possible elements, and we usually denote the universal set as U. This time it is the letter U. Every set must be a subset of the universal set. A universal set becomes important for the third logical operator. Remember our Boolean operators. It wasn't just and or, but we also had not, the negation. So we're going to look at what elements are not in set A. And in order to see what's not there, we need to know what all of the possibilities are. and that's the universal set. So if we specify that set A, 1, 3, 5, 7, 9, is in the universal set U, being 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, then the elements not in A would be 2, 4, 6, 8, 10, 11, 12. So we call this the set complement of A, and we write it as A star. So A star is the complement of A, and it's everything that is not in A that is in the universal set. So we're going to still do lots of examples with this. If it's not making sense right now, hopefully as we work through these, it will start to make sense. But we can also combine several set operations to form more complicated statements. So consider again the set A, 1, 3, 5, 7, 9. The set B as 1, 2, 3, 4, 5. And the universal set U as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. A intersection B star would be the intersection of A with the set of things not in B. There are two elements in A which are not in B. Seven and 9. How do we get that without examining? Well, A was the set 1, 3, 5, 7, 9. B star is the set of things not in B. So if 1 through 5 is in B, and the possibilities are 1 through 12, that means 6 through 12 would be B star, the complement of B, the things not in B. So to take the intersection of A and B star, it has to be in both sets, and only 7 and 9 are in both sets. And that's how we found the two elements in A which are not in B. You've probably encountered Venn diagrams as a brainstorming tool at some point in your previous studies. A Venn diagram is just two or more overlapping circles, which give you a visual space to compare and contrast two ideas. For example, we may wish to summarize a research project comparing apples and oranges. So one circle represents apples, the other circle represents oranges, and that overlapping space that's in both the apples circle and the oranges circle would apply to both. So for instance, just in the apples circle, not in the overlap, would be red and always has seeds. Just in the oranges circle, but not in the overlap, would be orange and available seedless. And then in the overlapping areas would be things that apply to both. Fruit grows on trees, may be eaten, may be juiced, sweet, just some of the things that apply to both apples and oranges. You know, they say it's like comparing apples and oranges, and they're two different things, but there's actually a lot in common between apples and oranges. Anyway, moving on. John Venn originally created his diagrams named after him in 1880 as a way of visualizing the interactions of sets. By the way, that's what eponymous means. It means named after the person. In set theory, a Venn diagram represents each set by a circle, usually drawn inside of a containing box, which represents the universal set. So this looks a little bit different than just the two overlapping circles. We have this box around it. And the box labeled U represents the universal set. And then our circles are labeled A and B to represent set A and set B. Set A is represented as anything inside the circle on the left. Set B is represented as anything inside the circle on the right. The overlap between the two circles are things that are in A and B. So that would be the union. I'm sorry. That would be the intersection, A intersection B. I was looking ahead to the next one and my eyes were focused on the word union. If we want the union, A union B, then it is in A or it is in B. So we fill in A and we fill in B, which includes the overlapping area, but it's not just the overlapping area. If it helps, union is a joining. We join together all of A and all of B in union. A and B, the intersection, are just where they intersect. Now, the box outside the circles, if we don't include the circles, then it represents anything not in either A or B. In other words, anything that is not in the union of A and B. In other words, A union B, in parentheses, star, the complement of the union of A and B. Venn diagrams become particularly useful for analyzing operations on three sets. Simply insert another circle for set C below the circles for sets A and B that we already have. So now we have circles for A, B, and C, and you can see there's many combinations of overlapping happening. The most middle area is the overlapping of all three sets, A, B, and C. Then there's an area that's just shared by A and B, an area that's just shared by B and C, and an area that's just shared by A and C. So, example one, using three sets and using Venn diagrams. Use a Venn diagram to visualize A intersect the union of B and C. For this example, our universal set is still the numbers 1 through 12. A is still 1, 3, 5, 7, 9. B is still 1, 2, 3, 4, 5. And we're introducing the set C, which is going to be containing the elements 3, 6, 9, and 12. rather than just play with the numbers, we're going to visualize A intersection the union of B and C on the Venn diagram first. And that'll help us figure out which elements we want. So since we want, and I moved it up to the top, A intersection union of B and C, first we'll see where B union C is on the diagram. That would be on the left here, this gray area. Everything in B and everything in C makes it into the union of B and C. We want this and the intersection of A. In other words, where do A and this union of B and C overlap? And the overlap would be in this darker area on the right. So we need the elements of A that are also in B, that are also in C, or that are also in both B and C. So elements of A that are in B, elements of A that are in C, or elements of A that are in both B and C. So our elements of A are 1, 3, 5, 7, 9. The ones that are also in B would be 1, 3, 5. The ones that are also in C are 3 and 9. We already had the 3, so we don't repeat it. Remember, we don't repeat elements. Once it's in, it's in. But the 9 is new. So the set 1, 3, 5, 9 would be in this darker area where A overlaps with B, A overlaps with C, and A overlaps with B and C. Example 2, same sets. This time we're going to use a Venn diagram to visualize the intersection of A and C intersected with the complement of B. So things that are in A and C intersecting with all of the things that are not in B, but are in the universe. So let's look at the two things that are being intersected. The intersection of A and C and B star. The intersection of A and C looks like this. It's where the A circle overlaps with the C circle. B star looks like this. Everything in the universe box that's not in the circle B. We want where these two pictures overlap. This gray area with this gray area. And spoiler alert, with the star in the picture, the area we end up with when we overlap the gray area from the left with the gray area from the right is this dark area right here. We need anything that is in A and C, but not also in B. The things that are in A and C would be 3 and 9, but it can't also be in B, and 3 is in B. So we throw the 3 away, and all we're left with is 9. Again, you don't have to use the Venn diagrams, but it was a lot easier to make two pictures and see where they overlap, and then find the numbers that are in the area that you want. Otherwise, you'd have to list out A, list out C, find the intersection, and then list out B star, the things not in B, and find the intersection between the intersection of A and C and B star. Remember, it's always more useful to come up with a picture. And this is a situation where we can simplify it a little bit by coming up with our pictures, in this case, the Venn diagrams. Instead of worrying about the specific elements of a set, oftentimes we'll only be interested in the number of elements that a set contains. This is called the cardinality of the set. And the cardinality of set A is denoted by n and then an A in parentheses. This is pronounced the cardinality of A, or the number of things inside of A, if you want to know where that n came from. Cardinality is just the number of things inside of. So if we consider new sets P, 1, 2, 3, 4, 5, 6, and Q, 2, 4, 6, 8, we can see by inspection that the cardinality of P, the number of things inside of P, would be 6, 1, 2, 3, 4, 5, 6 things. And the cardinality of Q, the number of things inside of Q, is 4, 1, 2, 3, 4 things. More interesting, we can also find the cardinality of the union and the cardinality of the intersection of P and Q. The cardinality of the union would be the number of things inside the set 1, 2, 3, 4, 5, 6, 8. And that's 7 things. The cardinality of the intersection would be the cardinality of 2, 4, 6. And that's 3. 1, 2, 3 things. Now, right away, you should see the so-called problem. And that is that there is no direct way to calculate the cardinalities of the union or intersection of two sets, given the cardinalities of the sets themselves. So just given that the cardinality of P is 6 and the cardinality of Q is 4, there's no way just from the numbers 6 and 4 to come up with the union having a cardinality of 7 and the intersection having a cardinality of 3. We would need the actual elements of the set to determine what's in the intersection, what's in the union, finding the intersection in the union, and then counting up the number of elements inside of it. For any two sets A and B, if you add the cardinality of A and the cardinality of B, the result is always larger than the cardinality of the union. This is because some elements get counted twice, namely those in the intersection. If it's in the intersection, that means it's in both. If it's in both, then you're counting it twice. So algebraically, we can say that the cardinality of the union is equal to the cardinality of the first plus the cardinality of the second minus the cardinality of the intersection. The things in A plus the things in B minus the things in both. In other words, minus the things that were counted twice undoes counting them twice, and we will end up with the number of things inside the union. So recall from the previous slide, the cardinality of P was 6, the cardinality of Q was 4, the cardinality of the union was 7, the cardinality of the intersection was 3. If we have our algebraic formula that the cardinality of the union is the cardinality of the first plus the cardinality of the second minus the cardinality of the intersection, that would give us 6 things plus 4 things minus 3 things, which is 10 minus 3, which is 7. And 7 was what was in the union. So it does check out. We can use Venn diagrams to help keep track of cardinalities when we're not given the actual elements of each set. Example 3. A survey asks 200 people, what beverage do you drink in the morning? And offers 4 choices. Coffee only, tea only, both coffee and tea, neither coffee nor tea. So those are the 4 options in the survey. Speaking of coffee, I'm going to refill that real quick. The screen may glitch black while I pause and restart, getting my coffee refilled in between. Excuse me real quick. Okay, I'm back. That shouldn't have done anything except maybe glitch black for a second. The results of the survey are that 20 people responded tea only, 80 people reported coffee only, and 40 people said both coffee and tea. Of the 200 people surveyed, how many drink coffee? How many drink tea? And how many drink neither coffee nor tea? We're going to figure this out with a Venn diagram. Now, again, the question is asking, of the 200 people surveyed, how many drink coffee? That doesn't mean coffee only. That would be the total of coffee only and both coffee and tea. How many drink tea is not asking tea only. It's including the tea only and the both coffee and tea. So let's go back to our 4-step problem-solving process. Step 1, understand the problem. It's important in this situation to recognize the difference between what we are given and what we are asked to find. That's what I just explained. Again, for example, we're given that 80 respondents drink coffee and not tea, in other words, coffee only. We're asked to find how many respondents drink coffee, whether or not they also drink tea. Step 2, devise a plan. We can think about these classifications as sets, and as sets, we can use a Venn diagram to organize the information we know. We build our Venn diagram around 2 sets, coffee drinkers and tea drinkers. The overlap will then be those who drink both coffee and tea, and those who drink neither coffee nor tea will be outside of the circles. Let's look at that Venn diagram in step 3 when we carry out the plan. We draw our coffee circle. We draw our tea circle. 80 drink coffee only. 20 drink tea only. 40 drink both coffee and tea. Since we know that there were 200 responses to the survey, there must be 200 minus the 80 that said coffee only, minus the 40 that said both, minus the 20 that said tea only, leaving 60 additional responses not accounted for. The 60 must be outside of the circles. They are still part of the universe, but since they're not within the circles, they must be outside of it. And now, sure enough, 80 plus 20 is 100, 40 plus 60 is 100, 100 plus 100 is 200. So we do have all of the survey responses accounted for at this time. This is also the answer to neither coffee nor tea. That was part of the question that we had to answer. So 60 there. The other regions we were asked about were how many people drink coffee, how many people drink tea. If we add together the 80 and the 40 to get the full coffee circle, that gives us 120 coffee drinkers. And if we add up the 40 and the 20 that make up the tea circle, that gives us 60 tea drinkers. So looking back at our result, making sure we answered the question, in total, 120 of the respondents drink coffee, 60 drink tea, and outside of the circles, 60 drink neither coffee nor tea. Of course, things quickly become more complicated when we involve a third set, as the next example shows. And this example has a lot of reading and comprehending involved. You may have noticed that this is definitely a reading comprehension sort of math class. Example 4. 50 students were surveyed and asked if they were taking a social science, humanities, or natural science course in the next semester. The responses tallied 21 students who were taking a social science course, 26 who were taking a humanities course, and 19 who were taking a natural science course. There were also 7 students who were not taking any of those courses. Of course, there is a good bit of overlap. Among the students taking a humanities course, 9 were also taking a social science course, and 10 were also taking a natural science course. There were 7 students who were taking both a social science and a natural science course, and 3 students who were taking all 3. How many students are taking a social science course, but not a natural science or humanities course? There is a lot to unpack here. Step 1, understand the problem. Since there are a lot of numbers to process, the important thing is to recognize that many of the categories given in this explanation overlap. Because we're asked specifically about students taking social science classes, again, it said how many students are taking a social science course, but not a natural science or humanities course. Because we're asked specifically about the social science classes, we can first filter only that information. We want to know how many students are taking only social science. 21 total students are taking social science. 9 are taking social science and humanities. 7 are taking social science and natural science. And 3 are taking all 3. Those numbers come from the big long problem. Step 2, devise a plan. No surprise, our plan is going to be using a Venn diagram with 3 circles, 1 for social science, 1 for humanities, 1 for natural science, and we overlap them. So carrying out the plan, we draw this out. Our 3 circles overlapping, which gives us 7 distinct areas in the circles, 8 if you count outside of the circle. Because we don't actually have a nice correlation between the numbers as given in the problem and these areas, we instead label them A, B, C, D, E, F, G, and H, and we'll replace these variables with numbers as we come up with them. So we're using variables instead of numbers because our information is not yet in a form that can be included. There's not a match. We're going to have to do some algebra to find what we need. Starting from the inside, we are given that there are 3 students taking all 3 types of courses. So that one is the one that is given to us. E, all the way in the center, can be replaced with 3. We're going to use the fact that E is 3 to translate some of the other numbers we were given into numbers that can be put in the Venn diagram. We're given that there are 9 students taking both social science, and humanities. In our diagram, the overlap between social science and humanities is represented by the total of 2 regions, B and E, which now are B and 3. So B plus 3 equals the 9 that we were given. If B plus 3 is 9, Some algebra tells us that b equals 6. So we can replace b with 6. Similarly, there are 7 students taking both social science and natural science. In our diagram, D plus 3 gives us the overlap between social science and natural science. And we're told that overlap is 7. So D plus 3 is 7. And some algebra tells us that D must be 4. So we can replace D with 4. Finally, we know that there are 21 total students taking a social science course. 21 would be everything in the social science circle. That is 4 regions added together. A plus 6 plus 4 plus 3. So A plus 6 plus 4 plus 3 is 21. That means A plus 13 is 21. And some algebra tells us that A must be 8. So 8 is what we replace A with. We were asked to find the number of students who would be taking only social science courses and not classes in the other 2 academic areas, which is the part of the Venn diagram shaded in this picture. It's the 8 that we just found. So looking back at our result, 8 students will be taking social sciences courses, but not natural science or humanities. Okay. Before the next video, be sure to try the Chapter 1, Section 3 homework in full. We will be going over every homework problem in the next class.